So another log-in efficiency of sorting technique is QuickSort. We use a divide and conquer algorithms, and we use recursions to help, right? By looking at the largest pile to sort, we divide in half, and the left half is always less than the right half, and keep doing that again and again, and make it smaller and smaller piles, and let's go until the small piles do not need to be further divided, which is the best case. So look at the methods. QuickSort, we pass in first and last index. Size is last match first plus 1. And best case is if size less than 2, do nothing. The general case, split the array according to splitting values. QuickSort the elements less than or equal to splitting value. QuickSort the elements greater than splitting value. So we just do the same QuickSort to the left, right, which is less than, equals, and to right, which is greater than again. So keep doing QuickSort on left and right, and keep doing split and do the same again and again. So it's very similar to merge sort technique, right? But it says it's going to save the space. So let's see how. We don't need to create a temp array. So QuickSort algorithm, if there's more than one element in values, right, from the array first to last, we're going to select and split the value. Split the array so that value first to splits point minus 1 less than or equal to split value, and the split point equal to split value. Now value split point plus 1 greater to the last greater than split value, and do QuickSort of the left subarray and QuickSort of the right subarray again. So the algorithm is depending on the selection value of the split value, where to split, right? We call it split value. This is used to divide the array into 2 subarrays. So how do we select the split value? So use the value in values first as the first splitting values. So that's the first time. Like for example, this is the list, unsorted list. We say split value is the value of the array at index first, which is 9. So split value is equals to 9. Now we just take that 9 and look through the list, right? And we only take the one that less than 9, right, to the left. So that means we move 8 and 6 to the left, and the one that's greater than 9 to the right. Now we get the pile that's smaller or equals to split value or split point, and we get a pile that's larger than split point. And we do again, right? Keep doing with the same 6 and 8. Then 6 is the first, right? Then it's very sorted. We're not going to do anymore, right? Less than 2, right? And we do again with this part. So 10, we have to have 11 to the left, and 10 and 14, 20 and 60. And 11 we no longer have to do. And then 14, 20 and 60 we pick 14. And then we have 20 on the left, 14 and 60. And no longer have to do, and at least it's sorted. So QuickSort, so this is how we implement it in Java. Pass first and last index. If first less than last, then we're still doing it. Find a split point, right? So that's function to find a split point, split first and last. And then we just do the same, call recursive, call itself, pass first and split point minus 1 and split point plus 1 at last. So it's recursive call itself until it's sorted. The split operation. So let's look at it again, right? Split value equals to value first, which is 9, right? So we have save f, so this is 9, and increment first until values first greater than split value. Increment first. Now split value is 9, so 20 is greater than 9, right? So decrement last until value last less than equal to split value. So last, that's why we stop it there. Last decrement until it's less than, so we stop it there. Now we swap, right? Swap the values of first and value of last. So 8 and 20. Now we move first and last toward each other. Then we move the first to the next one. And then increment the first until the value of first greater than split value. Same approach, right? So we move first into 10. And also decrement the last until the value last less than equals to split value. So keep the increment until 6. Right? So now we pretty much just found the location. We group them into the smaller piles and larger pile by looking at this approach, right? The split operation. Then it said first greater than last. Okay, if we check first greater than last, then that's it. We found that we already split it into two groups, so no more swap occurs within the loop. Then we just swap the values of save f, right? We make it like the index into the value of last. So we move 9 in between, so we split into two groups now. Then we have to arrange, right, the smaller piles from save f to last and the first to the end of the size of array. That's a larger one. Right, so we call split point pretty much when first 0 to split point minus 1. That's a smaller pile. And split point plus 1 to the size minus 1. That's the larger pile. If you look back at the algorithms, last, see that? So do a quick sort again. So that's the split algorithms. Get the split point. And you see that we no longer need to create a temp array. So when we analyzing this, every element in the array is compared to the dividing value, the split value. So the work done costs n. The array is divided into two subarrays, not necessary to be halves. So each of these pieces is then divided in two, and so on. If each piece is split approximately in half, they are log n. Okay, level of splits. So at each level we make n comparisons. So QuickSort is an big O of n log n algorithm. So drawback of QuickSort. We can see it's not always quicker. The log n levels of split if each split divides the segment of the array approximately in half. So as we've seen, the array division of QuickSort is sensitive to the order of the data. That is to the choice of the splitting value. So split value is the key. If the split are very lopsided and the subsequent recursively calls to QuickSort also result in lopsided splits, we can end up with a sort that is big O of n squared. Like for example, if you want to do a split sort on the sorted list already, it's going to give you big O of n squared. So what about space requirement? There can be many levels of recursions, right? So that's gonna cause some spaces of recursion, but it's better than merge sort that you don't have to create a temp array. So on average, the algorithm requires big O block n extra space to hold this information, and in the worst case requires n extra space, the same as merge sort. So QuickSort, despite the drawbacks, remember that QuickSort is very quick for a large collection of random data. Alright, so we're done with QuickSort. Another one is heap sort. That should give you n log n too.